All right, let's jump right into this explainer. Picture this, a little red car sets off on a road trip from point A to point B. Let's say the total distance is exactly 100 miles, and the trip takes exactly 5 hours. A quick mental calculation, 100 divided by 5, tells us the car was doing 20 miles per hour. Sounds simple, right? Well, hold on a second. This incredibly basic scenario actually opens up a fascinating mystery, one that literally forms the bedrock of modern mathematics. Because think about it, you averaged 20 miles per hour, sure, but were you actually going 20 miles per hour the entire time? No way! Think about any real road trip you've ever taken. When the car first started, it was going 0. Then it sped up. Maybe it hit a massive hill and lugged along at 10 miles per hour, or got stuck in traffic and just crawled at 5. Then, out on the open highway, maybe it cruised at 40. That 20 miles per hour, it's just an average of a totally messy, fluctuating journey. It actually doesn't tell us a single thing about how fast that car was going at any one specific frozen moment in time. And this hits the nail on the head when it comes to the difference between average speed and true speed. Figuring out an average for a whole trip, super easy, basic arithmetic. Total distance over total time. But what if we want to know the true, instantaneous speed of the car at one very specific, magical point on the road? Say, exactly as its bumper crosses mile marker 42? Finding the speed of an object frozen in a single instant is a much, much harder mystery. In fact, it's a puzzle that stumped some of the greatest minds for centuries. Section 1, the policeman's trick. Okay, imagine a clever highway cop wants to know your exact speed right at a specific location, let's call it point P, so he can hand you a ticket. He obviously can't use your entire 5-hour road trip average, so he tries a trick. He picks another spot, point Q, exactly 4 miles down the road. He clocks your car and sees it takes exactly 3 minutes to travel those 4 miles. Since 3 minutes is a 20th of an hour, he crunches the numbers and gets 80 miles per hour. Aha, he confidently declares you were doing 80 right at point P. But wait, are we absolutely positive the car was going 80 precisely at point P? Definitely not. During that 4-mile stretch, the driver could have started at 70, gunned it to 90, and just averaged out to 80. The reality is, the wider the gap between our 2 points, the more room there is for the speed to jump all over the place. 80 is really just a rough approximation. Section 2, the magic of limits. So, if a 4-mile stretch leaves too much wiggle room, let's just tighten things up. We can move point Q way closer to point P. What if we measure a tiny distance of just 0.1 miles? The average speed over that little sliver of road is going to be a much better guess of our true speed. And hey, we don't have to stop there. We can keep zooming in, shrinking the distance tighter and tighter, zeroing in on a more and more accurate read. Now, you're probably asking the obvious question here. If smaller is better, why don't we just make the distance exactly 0? Well, if the distance is 0, P and Q are the exact same point. That means 0 distance traveled in 0 time. And if you try to divide 0 miles by 0 hours, you get 0 over 0. That's a math dead end. The universe basically throws an error code, and we're left without a usable number. So, are we just stuck? Actually, scratch that, we aren't stuck at all. Here's the brilliant workaround. We don't actually need to set the distance to 0. We just change the question. Instead of asking what the speed is at exactly 0, we ask what destination are our numbers heading toward as that interval shrinks closer and closer to 0. If our calculations go from 80 to 84 to 85.5 to 85.99, we can see they're marching straight toward 86. We don't have to physically reach 0 to see where the map is pointing. To really wrap your head around this, picture a runaway train approaching a station. It gets closer and closer and closer. But what if it never stops? What if it just blasts straight through the station and keeps going? If it does that, the station wasn't its true destination. In math, for a number to be our true destination, what we call our limit, our calculations must not only get close to that number, but they have to stay infinitely close to it, no matter how tiny our margin of error gets. A limit is all about getting close and staying close. Section 3, the falling ball experiment. Let's actually test this zooming in theory on something real. Imagine dropping a heavy ball off a cliff. Physics gives us a beautiful, super simple formula for this. Distance equals 16 times time squared. So if we drop the ball and wait 2 seconds, we square the 2 to get 4, multiply by 16, and boom! After exactly 2 seconds, the ball has fallen a distance of exactly 64 feet. But here's the million-dollar question. How fast is that ball moving exactly at that 2-second mark? Your brain probably wants to take that 64 feet, divide it by the 2 seconds, and say 32 feet per second. But remember our little red car. That 32 feet per second is just the average for the whole drop. The ball started at 0 and accelerated the whole way down. We want the true freeze-frame speed right at 2 seconds. So let's deploy our shrinking trick. Let's calculate the average speed over a tiny window just after the 2-second mark. Between 2.0 and 2.1 seconds, the average speed is 65.6 feet per second. Let's shrink it. Between 2.0 and 2.01 seconds, it drops to 64.16. Shrink it again. From 2.0 to 2.001 seconds, it's 64.016. Shrink it one more time to just 1/10,000th of a second, and we get 64.0016 feet per second. Just look at that magnificent pattern. As our time interval gets insanely small, almost 0, the speed isn't just jumping around randomly. It is relentlessly honing in on one exact number, 64. That is our limit. The precise true speed of the ball exactly at the 2-second mark is 64 feet per second. We solved it. And we never even had to divide by 0. Section 4. Discovering the derivative. Now, mathematicians love absolutely bulletproof certainty, so let's use a little algebra to prove this trick works every single time. Instead of plugging in specific decimals like 0.1, let's just use the letter h to stand for our super tiny sliver of extra time. If we run 2 plus h through our distance formula, expand the algebra, and divide by our tiny time h, something awesome happens. The messy parts completely cancel out, and the whole thing elegantly collapses down to just this, 64 plus 16h. And this is the real aha moment. Just look at 64 plus 16h. What happens to that equation as our time interval, h, becomes infinitely tiny? Well, 16 times a microscopic number is an even more microscopic number. As h shrinks down towards 0, that extra 16h literally just melts away into nothingness. It vanishes, leaving us perfectly locked onto our true speed, 64. We've been using this incredible tool this entire time, so let's give it a formal name. A limit is the value that a variable approaches and remains arbitrarily close to as the variable changes. It's the ultimate destination our math points to when we zoom in, and it lets us bypass impossible roadblocks like 0 divided by 0. And here is the absolute best part of this whole thing. By asking a couple of curious questions about a toy car and a falling ball, and by using limits to shrink our intervals, you and I just successfully performed differential calculus. We found the derivative. A derivative is simply the instantaneous rate of change of one thing compared to another. It's true speed. Look, if you only take away one single thing from this explainer today, make it this equation. Average change plus shrinking the interval equals instantaneous change. Taking an average and shrinking the window you're looking through, that is the secret doorway that takes you straight out of basic arithmetic and into the pure magic of calculus. We started with a hypothetical red car, and we ended up unlocking the math that runs the universe. This exact concept of the derivative is what calculates rocket trajectories, predicts stock market crashes, and models how fluids move. Now that you've got the key to the magic of limits, what hidden secrets of motion are you going to unlock next?